Hi everyone, in today's video we are going to have a look at the first section of Unit 3 in Chemistry and Society, which are chemical calculations. And the first kind of calculation we're going to start with are excess calculations. First of all, as a little starter task, these are some calculations from National 5, just to get you started if you wanted to give these a go. The first one is to write a balanced equation for the complete combustion of methanol. To calculate the mass of 1 mole of methanol, and then number 3 is to calculate the mass of methanol required to make up 100 centimetres cubed of a 0.2 mole per litre solution when dissolved in water. So to make sure that you're ready to go into higher calculations, have a wee go at those three. So the idea of excess is something which is completely new. You've never seen this before in your study of chemistry so far. So let's try and put it into a kind of familiar context before we try and put it into a chemistry context. So if you are building a car, the number of cars produced relies on how many parts you have available to put together. So for every 1 car produced, you require 1 steering wheel and 4 tyres. I think everybody knows that already, hopefully. And there's a nice picture of a car. So the question is, if we had 2 steering wheels and 10 tyres, how many cars would be produced? So I want you to have a wee think about that and think of what your answer is going to be. With your 2 steering wheels and 10 tyres, only 2 of your cars could be produced. You have an extra 2 tyres, so we would say you have an excess of tyres. Your 2 steering wheels pair up with your 8 tyres to make 2 cars, and you have 2 more tyres than you need. In other words, you have 2 tyres left over. That's what we would call an excess of tyres. So, from this scenario that we've just had a look at, to determine how many cars are produced, we must look at whatever one of the reactants is not in excess, as that limits the reaction. If we had looked only at the tyres, we'd have said, right, well, we could maybe make 2.5 cars with 10 tyres, but we can't make 2.5 cars, because if we were to make 2.5 cars, theoretically, obviously, we would need 2.5 steering wheels, and we only have 2. So with the only steering wheels we have available being 2, they pair up with 8 tyres to only produce 2 cars. So the point of this is to realise that to determine how much product you're getting out of a reaction, and in this example that would be the number of cars produced, you must look at the reactant which is not in excess to do that. This will hopefully make a wee bit more sense once we start practicing examples. So here is a kind of chemical example now. Imagine you are in the classroom, in the lab, and you have some magnesium ribbon and 2 moles per litre hydrochloric acid. You've got your acid in a test tube, and you've got your magnesium ribbon in a wee tub. Number 1, the question to consider is, how could we ensure all of the acid reacted? What would we have to do to make sure that every single molecule of your acid has reacted? Number 2, if we were to try and calculate the mass of salt produced in the reaction, which reactant would we use in our mole ratio? And the answer for that's already there, so let's just go through the answers. So how could we ensure all of the acid has reacted? What you would have to do is you would have to hold your test tube of acid, and you would need to keep adding magnesium. Now, what you're doing there is you're adding an excess of magnesium, and that means you're going to keep adding more and more and more until no magnesium dissolves. In other words, when you see extra pieces of magnesium floating in the acid that are not dissolving, that means that you have extra magnesium and that every single bit of your acid has reacted. If you wanted to calculate the mass of the salt produced, now we know that we've added excess magnesium, so our limiting reactant, the reactant that limits how much product we would produce, is the hydrochloric acid. So if we were using a mole ratio and we said 1 mole of hydrochloric acid produces 2 moles of salt, that's what we would use, not the magnesium. So the first example, hopefully this will tie in what we've learned so far. In a reaction, 6.216 grams of lead is added to 50 centimetres cubed of 1 mole per litre hydrochloric acid. So part A of this question is to calculate which reactant is in excess, and B is what mass of hydrogen gas will be produced upon completion of the reaction. So there are a certain number of steps we are going to follow. These steps are exactly the same in every single excess calculation you will encounter. So as long as you learn the steps and follow them correctly, you should have no problem with these calculations whatsoever. So, step 1, obviously when you do any calculation, it is always useful to write down your equation. But what you want to do for step 1 is calculate the number of moles of the left reactant. So always start with what's on your left. Now on our left here we see we have 1 mole of lead. So what we're going to do is we're going to go ahead and calculate the number of moles of lead that we have. Now in the question it told us that the mass of lead we had was 6.216 grams. To calculate the number of moles, we would do the mass divided by the GFM. The gram formula mass of lead is 207.2. If you work that out, you end up with 0.03 moles of lead. Now, these are the same examples that are in your notes booklet. So while we are going through these, it would be helpful for you to note them down as we go along. And then, of course, at the end of every video, there are some questions for you to try and pause and mark yourself. But these, hopefully you can write down as we go through. So step 1 is always calculate the number of moles of the left reactant. Our left reactant is lead. We have 0.03 moles of lead. Now for step 2, we're going to compare the number of moles to determine how much hydrochloric acid we need for the reaction. So if we look at our mole ratio, 1 mole of lead needs to react with 2 moles of hydrochloric acid. It's a 1 to 2 mole ratio here. So that means if we have 0.03 moles of lead, we require twice that amount. So it's 0.06 moles of hydrochloric acid. That's how much hydrochloric acid we require for the number of moles of lead that we have to react successfully. Step 3 is to say, well, we need 0.06 moles of hydrochloric acid, but how many moles do we actually have? Because we might not have enough, or we might have too much. So let's calculate this now. I also find it helpful to calculate the number of moles of the left and right reactants directly underneath so that I can keep track of which one is my left reactant and which one is my right reactant. So for this, then in the question we were given a concentration and a volume. This is where your National 5 knowledge really comes in super handy. Your number of moles equals concentration times volume. Your concentration is 1 and your volume is 50 centimetres cubed, which ends up being 0.05. Remember to convert your volumes from centimetres cubed into litres. So when you figure out that calculation, you have 0.05 moles of hydrochloric acid. So we required, go back a wee second, we required 0.06 moles to be present in the reaction. We don't have 0.06 moles, we only have 0.05. So this is just added additional information, you don't have to write this down, but what that means is if we only have 0.05 moles of hydrochloric acid, if we go backwards, it's a 2 mole to 1 mole ratio, then that means that we need 0.025 moles of lead. If this is not enough, then that means that we have too much lead. So our final step is to write our statement for which reactant is in excess. So which reaction we have too much of. If we required 0.06 moles of hydrochloric acid, but we only have 0.05, then we don't have enough of that. So that means that the other reactant, in this case lead, we have too much of. So all you're going to do for step 4 is just say Pb, or lead, is the reactant in excess. You don't need this extra bit here, I've just put that in for extra information. So only 0.25 moles of the lead will react with the 0.05 moles of acid. But in your final statement, all you have to say is lead is the reactant in excess, because your calculations show that you know why that is the case. So 4 steps, and that is us solved part A of the question. Now remember, there's a part B. Part A is just calculate which reactant is in excess. Part B is what mass of hydrogen gas will be produced upon completion of the reaction. Now remember, back to earlier, I said if you were to determine how much product is produced, you must use the limiting reactant. In other words, the reactant which is not in excess. Our limiting reactant was hydrochloric acid, and we calculated that we had 0.05 moles of that. That's how much we actually have. So what we do is we use the mole ratio, so 2 moles of hydrochloric acid produce 1 mole of hydrogen gas, to find out how many moles of hydrogen gas we have. So if you react 0.05 moles of HCl, you will produce 0.025 moles of hydrogen. Using the number of moles, we can calculate the mass by multiplying the number of moles by the GFM. Hydrogen's GFM is 2, multiplied by 0.025, we end up with 0.05 grams of hydrogen produced. So the only new part of this calculation is really to understand where the numbers are coming from. The actual calculating the mass and the number of moles is, or should be, extremely familiar to you, because we use that a lot at National 5. Okay, let's have a look at example 2. In a reaction, 20 centimetres cubed of 0.2 moles per litre barium chloride solution is added to 50 centimetres cubed of 0.2 moles per litre sulfuric acid. Calculate which reactant is in excess is part A to the question, and part B is calculate the mass of precipitate produced. So this is a wee bit different from our example 1, and that both of our reactants are solutions. So we will be using the N equals C times V triangle to calculate the number of moles of both of our reactants. So first of all, again, write down your equation and your mole ratio of your reactants. Then step 1, as always, calculate the number of moles of the left reactant. The number of moles of barium chloride that we have, we work this out by doing concentration times volume, which is 0.02 times 0.02, giving us 0.004 moles. Step 2 is to compare this then with the number of moles of sulfuric acid. If 1 mole of barium chloride reacts with 1 mole of sulfuric acid, then 0.004 moles of barium chloride requires 0.004 moles of sulfuric acid. Step 3 is to calculate how many moles of sulfuric acid we actually have. Again, we're using the C times V triangle. So we have 0.02 times 0.05. We have 0.01 moles of sulfuric acid in our reaction. We don't need that much, we only need 0.004. So therefore, step 4, our sulfuric acid is the reactant in excess. So I know we have 0.01 moles of this, but only 0.004 of it will react with the number of moles of barium chloride we have, meaning that there will be an extra 0.006 moles of the sulfuric acid left over. Now again, I'm just putting that in there to help you hopefully better understand where the numbers are coming from, but all you need to say in that situation is sulfuric acid is the reactant in excess, full stop. So that is part A. Part B is to calculate the mass of the precipitate produced. Now, from your knowledge in National 5, you should know that the precipitate is going to be the solid that is produced in this reaction. So if we go back to the equation, we can see that that is barium sulfate. Now, which of the reactants are we going to use for this? We're not going to use the sulfuric acid because we said that it was in excess. So we're going to use the mole ratio of the barium chloride to the barium sulfate. So 1 mole of barium chloride produces 1 mole of barium sulfate. We had 0.004 moles of barium chloride reacting, so that means we're going to have 0.004 moles of barium sulfate produced. To calculate the mass of that precipitate produced, we're going to do the number of moles multiplied by the GFM, which is 0.004 times 233.4, giving us the number 0.9336, and then we can round to 2 decimal places for a mass of 0.93 grams. Example 3 is a little bit trickier than the first two. We're still going to use the same steps, but this requires a much deeper understanding of excess and what is actually going on in the reaction to solve parts B and C as well. So let's read through this together. In a reaction, 1.59 grams of copper 2 oxide is added to a beaker containing 50 centimetres cubed of 0.24 moles per litre sulfuric acid. The mixture is heated and stirred until no further reaction, and the contents of the beaker are then filtered. So this is the procedure, I don't know if some of you have noticed this already, for making crystals. Now hopefully everybody has been able to make copper sulfate crystals before. If you haven't, then that's okay. If we ever get back into the lab, we can maybe do it one day. But if you've done it before, that will certainly help you kind of visualise the steps in this reaction. The calculation for part A is exactly the same as it always is. So let's have a look at our balanced equation. We can see that 1 mole of copper oxide reacts with 1 mole of sulfuric acid. As always, step 1 is to calculate the number of moles of the left reactant. Now we've got a mass this time, so we're going to do mass divided by GFM. That gives us 1.59, that's the grams of copper oxide we have from the question, divided by 79.5, which is the GFM. That gives us 0.02 moles of copper oxide. Step 2 is to see how many moles of sulfuric acid are required. If we have 0.02 moles of copper oxide, that's going to require 0.02 moles of H2SO4 because we're in a 1-to-1 mole ratio. Step 3 is to calculate how many moles of sulfuric acid we actually have. So this time we're going to have concentration times volume because that is the quantities we are given in the question. One is a concentration, one is a volume. So we have 0.24 multiplied by 0.05 to give us a number of moles of 0.012. If we look back, we required 0.02, we only have 0.012, therefore we don't have enough sulfuric acid, we must have excess copper oxide. Now, if you think back to doing this experiment in third year, if you can remember that far back, that is exactly what you have to do when you carry out this experiment. You need to add excess copper oxide. It is a green powder, and you keep adding it to the acid until you don't hear any fizzing, and that means that no more has dissolved. So even though you didn't know what excess was at the time, you have certainly practiced this before in the lab and just not really understood fully why you were doing it. But this hopefully makes sense now. So that is only section A of this question. We have a part B and a part C. So let's revisit what part B is. So B asks us to calculate the mass of unreacted copper oxide, which would be removed from the beaker by filtration after being dried. Now, not all of that 1.59 grams of copper oxide is going to react, and we want to calculate how much of that is going to be unreacted. So what we need to do here is we have to look at our mole ratio of copper oxide and sulfuric acid. So we calculated that we only had 0.012 moles of sulfuric acid. That means only 0.012 moles of copper oxide could react because it was a 1-to-1 mole ratio. If we actually have 0.02 moles of copper oxide, then that means that only having used 0.012, we have 0.008 moles of copper oxide left unreacted, so it's just sitting there. If we want to calculate the mass of 0.008 moles of copper oxide, we can use the mass equals number of moles times gram formula mass triangle to come up with 0.64 grams. That's part B. Part C, the remaining solution is evaporated and dried. What mass of anhydrous copper 2 sulfate would be obtained? So that is just asking when we have evaporated and dried the crystals with no water in them, that's what anhydrous means, how much copper sulfate will we have obtained? So this is where we're going to use the limiting reactant to calculate how much product, which is copper 2 sulfate, we would have produced in the reaction. So the limiting reactant, since the copper oxide was in excess, is going to be the sulfuric acid. 1 mole of sulfuric acid produces 1 mole of copper sulfate. We only had 0.012 moles, so that's going to produce 0.012 moles of copper sulfate. To calculate the mass of the product produced, again, we're going to use the triangle, number of moles times gram formula mass. The gram formula mass of copper sulfate is 159.6. The number of moles we had from our mole ratio here is 0.012. Therefore, we have 1.92 grams of copper sulfate produced. There is a wee G missing there for grams. That should be there. Okay, so we have 2 questions here. Now these are of the more simpler type questions where all you have to do is calculate which reactant is in excess. I want you to be able to do that step first, and then we will look at some more difficult problem solving type questions in our tutorial, which we're going to have next week. So in each of the following reactions, calculate which reactant is in excess. So you have A and B. Pause the video, give these 2 questions a go, and then unpause and we will go through the answers together. You can self-mark these. Okay, first one then is zinc. We have our equation here, and step 1, as always, is to calculate your number of moles of zinc. In the question, we were told that we had 6.5 grams of zinc, so we're going to be using the mass and GFM triangle. So we have mass divided by gram formula mass to give us number of moles, 6.5 divided by 65.4, and we get 0.994 moles of zinc. You could at this point round that up to 0.1. I've just left it as it is. It doesn't really matter. So, step 2 is to say if we have 0.994 moles of zinc, how much sulfuric acid does that require? 0.994 moles of zinc requires the same, because it's a 1-to-1 mole ratio, 0.994 moles of sulfuric acid. Step 3, how much sulfuric acid have we actually got? We have concentration times volume, 2 times 0.025, which gives us 0.05 moles. Now that is not enough. We require 0.9 moles, we've only got 0.05. So that means, step 4, that zinc is in excess. There are 2 marks available for excess questions. The first mark comes from calculating the number of moles of each reactant, so that would be your 0.994 and your 0.05. The second mark comes from a statement to say which of the reactants is in excess, but it's paired with this step 2 here. So showing that you require this much sulfuric acid, you don't have enough, therefore the zinc is in excess. If you always lay out your excess questions as shown, then you'll always get 2 marks for them, obviously having done the calculation correctly. Second example then is magnesium. This time we have magnesium and hydrochloric acid to give magnesium chloride and hydrogen gas. Which of the reactants is in excess? Again, step 1, we always calculate the number of moles of our left reactant. In this case is magnesium. We are given a mass of magnesium of 2.4 grams in the question. The GFM is 24.5, which gives us 0.1 moles. Step 2 is to look at our mole ratio. Well, 1 mole of magnesium requires 2 moles of hydrochloric acid, so 0.1 moles is going to require 0.2 moles. How much hydrochloric acid do we actually have? From the question, our concentration is 1, our volume, remember to change to litres, is 0.1, which is going to give us 0.1 moles. So we only have half the number of moles of hydrochloric acid than is required, which is not enough. That means, step 4, that the magnesium is in excess. Hopefully you found this video useful. If you don't or are struggling to have a solid understanding of the theory behind excess and why it's important, then my advice to you would be to work on getting the 4 steps into your head first of all by practicing as many questions as you can. We are going to have past paper questions up on the Google Classroom, which we are going to go through the answers to in one of the tutorials in the following week. So make sure that if you're struggling with this, the first thing you do is you learn all 4 steps and you practice it as much as you can, because chances are the bulk of the marks of an excess question is going to be calculating which reactant is in excess. When we've kind of got the basics down, we can then start looking at the more problem-solving type questions where you're having to really think about what's going on in the reaction to calculate the mass of products produced, etc. Hopefully that was useful, and I'll see you all in the tutorial.